Lisa will start it. Okay, and we are live for coffee and compressed air. Today we have a episode, Thanksgiving episode of the week for all our American colleagues. So this is why we are on live on Tuesday. And I actually have today coffee with me because it's finally for me 10 a.m. But I have a special guest, Murray Nottle from Australia. So Murray, probably for you it's not it's not a coffee time yet.
No, it'd be more a nightcap rather than a coffee, I'd suggest.
Yes, and
Yeah.
Today we have I would say a very hot topic. It's a compressed air efficiency because there are so many myths. Some of people are telling, let's replace by electric drives because efficiency is below 5%. Other one are saying it's a 300%, 200%. And it is so overwhelming, especially for end users, for people that are working with the compressed air, not on the daily basis, to understand where we are at what is the standpoint. And I must say there are many different opinions, and we might have also different opinions, but today the stage is yours. So I would like to get your experience on that, and maybe you can just present yourself and tell about all your years of experience in compressed air and what is your opinion on the efficiency.
Yeah, thanks for that. So I'm an engineer based in Melbourne. I've been in compressed air over 25 years, sales support with pneumatic companies, compressor companies, and I've been consulting for over about 15 years or so. And when people ask me what I do, I say I worked with compressed air. It uses about 10% of the power used by industry, and they use it really badly, so I've got a job. Which is fairly fair and true. The reason why I said I'd come on this episode was because about a month ago you had another Mythbuster session, and I put up, well, compressed air efficiency, let's tackle that myth. And you said, yep, let's jump on board. And the reason for that is because there's been lots of guides and material published on a lot of opinion that says that the air compressor is only 5%. That all of the energy is taken out of
or components.
You'll find guides that say that air compressors are only 5% efficient. And, and part of what they've done is that they've taken the heat, the power you put in, take out the heat, where you cool it back down to 10 or 15 degrees above ambient, and say that's all the energy that's left in the compressed air. Now, they're totally ignoring several things there. One is that compressor's got pressure. It can do work. It's more than 5%. You can take a data sheet for a compressor. You can take a data sheet for an air motor. Look at the two, and the air motor is 10% efficient compared to the power going in from the compressor. So there's obviously things wrong there. The other thing that they're doing is they're only viewing the compressor on its own. A compressed air system is actually a cycle. You take air in, you compress it, you cool it, and when you compress it, that heats it up. You cool it so you can use it, and when you expand it, the air cools down as it expands, and that cold air then absorbs heat from the atmosphere and the area around it to warm it back up to the starting conditions. So it is a complete cycle. It has to be viewed as a cycle. So to say that the compressor is 5% efficient without considering the efficiency of everything that's using the air is just totally wrong. Sure, we can look at how efficient the compressor is compared to the ideal. So say a rotary screw compressor, they're typically 60 to 75% efficient compared to the ideal, say an isentropic compression. Expansion, how are you expanding it? Every single little device is different. So you could take an actuator where you've just got, it effectively runs at constant pressure. It will use about 26% it will deliver about 26% of the power that goes into a compressor. Now, that's assuming that the actuator is at 7 bar. It's never at 7 bar, which is what the compressor is putting out. You've always got losses, so it gets less and less. So, yeah, you could have a system which is only 5% efficient, but it's well beyond what the compressor is. It's not due to what the compressor is putting out. With the compressor, if we go back to pure theory for a bit, when you compress the air up to 7 bar, so you're doing it in a single stage piston compressor, the air coming out of that gets up to about 250, 260 centigrade. You cool that back down to ambient. Cooling it down reduces its volume to about the absolute temperature ratio, so about 55, 56%. The amount of power used when you compress and when you expand depends upon your volume, your starting volume. So if you've got 57% of the volume when you expand that, you can get 57% of the power out that you theoretically put into the compressor. Now, that's a theory. And people ignore that. So that is the theoretical best you could do. When we come to look at how the actual efficiency of the system, you've got the theoretical efficiencies, you've then got design choices, you've then got operational choices as to how that efficiency gets made worse. Some of that, the design choice, you buy a cheap and nasty compressor that's not very efficient. That's a design choice. You put in undersized piping, that's a design choice. You put in nice big piping and nice general stuff, that's a design choice which affects your efficiency of your system. Operationally, you've also got that same scenario. Are you running the compressors in their right combination? People that have seen some of my presentations and worked before will know that I've done surveys where you've got one compressor is using twice the power of another compressor at the same flow rate. They're just running on different days of the week, but the flow rate was the same. So it's a matter of just making sure you're running your gear properly. Leaks. People often blame leaks on the efficiency of the system, but that's an operational choice. That's up to the site to decide whether they want to let those leaks go. I've measured sites where the leak rate, or I call it non-productive air demand, because there could be other stuff happening, is only 2 or 3%, albeit a small system, but 2 or 3%. I've done other surveys where it's been 70, 75%. And that has a huge impact on what the efficiency of the system is, but that's an operational choice by the site. So where we get to is when someone says all he can get is 5% out of the compressor, no one's going to try and do anything better. No one thinks there's an opportunity to do any better, whereas in fact there is a huge opportunity to do better. We've covered that, and that's part of the reason why I've come on, because we need to address that myth. Yes, it can be that bad, but there's design choices, there's operational choices that can make it a whole lot better. Our simple actuator, we can change how that expands. Instead of running constant pressure for the whole way through, you can cut the air supply off to it halfway through, and it will actually expand into the cylinders. Uses less air, depending upon what you need force-wise at the end of the cylinder, at the end of stroke. You adjust where you cut the air off. You need some back pressure on it for speed control, yeah, but there are ways and means that you can, with your designs, you can make things better. I've done what I call equipment design reviews, where I actually do high-speed data logging, redesign the pneumatics on machines. I've measured savings of 80, 90% on machines that I've changed and upgraded. Now, if I'm getting 80, 90% saving in air consumption for the same production rate, actually faster production rates, how woeful was that efficiency beforehand? It was just absolutely shocking. Yes. And that's a simple design choice. Redesign the machine, you can get those sort of savings. So are we 55% possible efficiency out of the pneumatics because that's a theoretical maximum? No, we've just said that the air compressors are only 65 to 75%. So that's going to come back down to about 40%.
Murray, I think it is a very good point what you're just saying, that it's not a theoretical maximum when people say it can be 5 or 10%, because usually systems are bad sized, and this is why we have a lot of job in compressed air. Because once I had a project where we reduced by 80%, but not the consumption of entire plant, but not because were geniuses or it was some crazy system. It was something fascinating there, because the system was so badly designed. It was just extremely badly designed that, and of course I cannot use it in my use cases, usually my presentations, because it's not the best use case. It's the best use case for 80%, but the system was already badly designed, so it's less credible, and this is the problem. And as you say, very great point, it is not a theoretical maximum, and this is where all this theory comes in, the boundaries come in. Extremely important to remember, if we go into the actuator side, you can always design correctly the actuator. You can reduce pressure on the backstroke, use the expansion energy, so reduce the volume for each actuator, right? You can reduce for the blow-on applications, you can rethink your vacuum applications completely. At the end, arriving to we need to see the systematic approach. I think I have just one question, and it is my personal curiosity, because I spoke with some people from the compressor air industry, and I thought that because I come from the demand side, my side is in pneumatics, so now I'm crawling very slowly into the compressor world, the compressor room itself. A lot of compressor suppliers are telling that the compressor suppliers telling the compressor efficiency is either 0 or 100 because it works as a heat pump. So and I mean, there is still a part that actually creates the pressure. So let's say this useful energy that can be then transferred into the energy of the moving mass in the cylinders, into the impact energy of the flow. So it is not everything goes into the heat, but there is a lot of things that I can find on internet that is really, it is either 0% efficiency or 100% efficiency. What like, have you heard about this? What is your take on that? Because I think this is one of the very misleading information.
Well, and this is okay. There's several aspects here. There is how efficient the compressor is compared to its theoretical value, and that's probably the only time I'd use efficiency when referring to the compressor as an isolated piece of equipment when it's not in the system. You could. If you can consider it as a heat pump, as a source of heat, a compressor is 100% efficient as a source of heat, because you can set it up that way. If you cool the air back down to ambient, or if you're, say, doing heat recovery into town water and you're on a hot day, you'll have 105% because you're actually cooling the air that you're pulling in to heat up the water. So it depends upon how you define or what you're referring to the efficiency as. With an air compressor, it is a heat pump. The compressed air cycle is a thermodynamic cycle. You heat the air, you cool it, you expand it. As you expand it, that cools it more. You take heat out at a high temperature, you suck air back into a low temperature. It is actually a refrigeration cycle. The first refrigerators used on ships back in the 1800s were air cycle refrigeration. Use air as the working fluid in their refrigeration systems. Your jet aircraft air conditioning systems use a compressed air cycle for their air conditioning systems as a refrigeration system. So I talk about a compressed air system as being an open source heat pump, which surprises some people. But if you're in a food manufacturing facility, you'll need hot water, you'll need cold, chilled water. Depending upon how you operate your compressed air system, you can take all of that compressor heat out. You still get work out of the pneumatics from the compressed air. You may or may not be able to capture the cold air coming out of the pneumatics. It might be there a little bit on the side because it's cooling your production spaces, depending upon where it's exhausting. That waste heat coming off can be used to drive absorption chiller heat pumps. So you could get an extra 0.6 of heat into your hot water that you need. You'll also get 0.6 of your compressor heat as chilling. And that all adds up to contribute to the site services and reducing the power bill for the site services in those factories. So it's hard to say what the efficiency of a compressed air system. You can't. It's not hard to say. It's impossible to say.
It is. I think like the problem is also lays in the definitions, right? Because I worked always with the terms like the exergy. It's basically the energy that can be transformed. So it's, let's say, high grade energy. So you have the can be transformed into the pressure. It can move the cylinders. It can, as I said before, to create the kinetic impact energy of the blowing. So it can work and it can do mechanical work, right? The heat cannot be then transferred into another form of energy. So it is a low grade energy. And if we look at it doesn't mean it's like bad or good. It's just a low grade energy that it's not an exergy. So it's considered as a loss, but then that can be also reused further ahead. And I think in the compressor industry, I don't see at all this exergetic analysis in terms of what is the useful energy for the mechanical purposes. And because I was asking the suppliers, it's like, okay, how you explain the creation of the pressure levels then to be transformed into the mechanical energy? Like, it's like whatever, it's like 0 or 100%. And then you have a heat, you have such a huge potential of the energy that you still can reuse for other processes. And as we discussed with you also in the message, in other conversations, that it depends on where you set the boundaries and what you define as efficiency. Because very often there is this confusion, because since heat is a low grade energy and heat pump actually moves the energy, it's not generates the energy from the environment, from the electricity. It moves this energy by having this circle inside it. So you have the higher coefficient of performance, right? So you have this like 200% coefficient of performance, but it's not efficiency because it's not the heat can do any work there. So it's not something that you can compare output with the input of the electricity, because you pay more for electricity rather than pay you there. So it will be very weird to use a compressor as a heat pump, because you pay for electrical energy to get the mechanical output out of this after all the transformations. So, and I think to define what is, very often I see that the coefficient of performance is considered as the efficiency. Or if you have a compressor and then you have the heat recovery after that, the recovered heat then compared to the electricity energy. So you have somewhere 200 kilowatt recovered, 200 kilowatt of electricity input, but it's not 200% efficiency of that, because you can't compare heat with electricity. So this kilowatt, this is at least like in my world. I know what is your opinion on that?
Well, and again, it's a perspective thing. As an engineer, and I said this earlier, that the air compressor as a source of heat can be 100% efficient. And that's I wouldn't say it's a high grade heat, but it's not a very low grade heat either. You can say for a screw compressor, you can take your heat off at 90 to 95 Celsius, depending upon what you bring in. If you're heating hot water from the town water supply, 15 degrees, 95 degrees, set it up properly, you can do it. With the thermal drive chiller I was talking about, you can get that 0.6 because the hot water you're then delivering to the site is, say, at 60 degrees. So the energy efficiency goes down. So as an engineer, it's coefficient of performance, absolutely. That's the ratio of energy that you should be using the energy into the energy being delivered. From a businessman or an accountant's point of view that don't know what CAP is and that's lost of them, they'll have a look at 100% of their energy going into the air compressor, and they'll see that it's providing 300% of its site utilities. So the CAP might be 3, CAP might be 2, but he'll see it as at that ratio. Excuse me. So he'll say it's, oh, wow, I've got 100% in and I'm getting 200 or 300% out, because that's his way of working with ratios. So again, it's a different perspective. So is it energy in, energy out? No. But is it power saving for energy in? Potentially, yes. And so that's where we had some fun and games with offline chats where we're going, well, you know, we could be 200%, we could be 300%, but it depends upon your perspective as to whether you're looking at and how you're defining your efficiencies. With a heat pump, there is the Carnot efficiency, so the idle efficiency for the heat pump. And then you've got, as we said with the air compressors, how efficient is the heat pump compared to that theoretical maximum? And again, if we're looking at the individual components of a system, all we can do when we're talking about their efficiency is look at how good they are against their theoretical maximum. And that's where the knowing what the theoretical maximums are and the theoretical minimums gives you something to aspire to. The realities, we know they're not there, but it gives you some, it opens up the boundaries. You don't feel restricted to 5%. You don't feel restricted to 25%. You know that, hey, well, I can theoretically go up to this. And depending upon how I use the heat, I might be able to get more. Depending upon how I do the work with the pneumatics, you can cascade it through. That air, once it's finally exhausted, is cold. It's also very dry. So it could be brought back into your compressor room for purging your desiccant dryer or a membrane dryer without actually using fresh compressed air to do that. So air reuse schemes are greatly underutilised, but that air has got other properties apart from just being at pressure or hot or cold. It's also, by the time it comes out the exhaust, it's also very dry. So how do you work out the efficiency of a system where you've got so many, the efficiencies of all the individual components that are using the air? And that's why it's impossible. But don't be blinkered by thinking, you know, you can only get 5%. Have your eyes open that maybe you could get 40%. You might be able to play around and get even better. Unlikely, but at least you can aspire to do that. And as we've said, both said, we've done projects where we've had 80% plus air savings. And you change your compressor settings and all of a sudden you've got twice the air savings. So to say that you're going to approach a theoretical limit, you're probably that far off it, it becomes irrelevant. You are probably down at 1 or 2% for a particular process, but you've got this huge opportunity to improve it and going forward, and it will make a real difference. And don't think, oh, you know, maybe I'm at 2% or 5%, I'm not going to do any better. No, you won't be near that. And so there is a huge opportunity to do much, much better.
Yeah, and I think it also comes into the whole systemic approach, right? From the demand side distribution and the compressed air room, because unfortunately our industry is extremely fragmented. So it's either compressor room or it's either few pneumatic components. But when, for example, I had my projects when I worked as a researcher and we worked with the companies that were doing the machines, the production lines, and we developed like some methods for energy savings circuits for pneumatic cylinders there. Then I was very upset. I saw it in the whole production because if you don't adjust the compressor to the changes there, nothing changed. So the same thing also if you work only in the compressor room, nothing is going to change usually in the pneumatic. Maybe a little bit on the terms of yes, you put one more efficient component, one more efficient compressor, a little bit adjustment of control, this will change. But if you don't work into the system holistically, nothing. It's not very sustainable.
No. And my customers know when I do a logger survey, I'll have the power meters, I'll have the pressure transducers, I'll have flow coming out of the compressor room.
Yes.
But I also say to the customer, what's your critical point of use? What is the first machine to be affected when you haven't got enough pressure? And they'll know exactly what it is. And so we'll put a pressure logger there and maybe a couple along the way back. And when we come to do demand side work, we'll go to that machine and what are the pressure drops getting to that machine? I've got a project on the go at the moment. We'll be hopefully retrofitting some bits in 2 or 3 weeks. And we were seeing 7 bar system, and we were seeing 4 to 4.5 bar on the manifolds inside the machine before it actually starts to supply the pneumatics. And all of that has just been lost across the isolation valve, the filter regulator, undersized tubing, safety isolation valves to actually get it into the manifolds before it can actually supply the pneumatics. And at one point, a variable speed compressor stopped, and a fixed speed machine, which ended up operating a bit unload, and you could see the sawtooth pressure profiles in the manifold. So there's no regulation in the system getting to it. And ironically, when you're getting to the peaks of the load cycle, the machine would actually start to have hiccups because it's getting too much pressure.
Yes.
And so it's using more air, it's slowing it down, it's having hiccups, and all because we've got this pressure drop getting into the machine. But if we hadn't had that pressure logger there, we wouldn't have known what the pressure drop was to get down there from the compressor room. So it's that holistic approach. I'm lucky, I guess, that I did time in pneumatics, and then I was with a compressor company. And you talk about compressor companies not thinking about the production space. The service techs are lucky to think about the dryers and the filters, let alone all their focus is on the compressors. So it's a black art. When I was at pneumatics, we weren't told anything about compressor room efficiency, or we might have got a little bit of stuff on piping. We got a little bit of stuff about dryers. But yeah, as you say, it's a very fragmented industry. I'm lucky I've had experience in both sides, but yeah, to drive it forward, people really need to understand both sides. I know some of the other people, our associates in the USA, some of them have got experience in both and work in both. But yeah, they're pretty few and far between, that's for sure.
Yes. Now, Murray, that's really extremely interesting discussion. So unfortunately, our coffee is usually like now, before it was 15 minutes, now 20, now 30, but it's not about just like to give more in depth. So I'm sure that we have more talks in depth, and we'll put it on YouTube. So please follow also Murray for more insight into the Australian industry of compressed air, from the demand to the compressor room. And I always tell compressed air is the demand-driven system. So I always say from demand to compressor room and not the other way around. And I'm sure that we continue the conversation about the efficiency, and we were busting more myths around it. And I really appreciate, and I love the way that you say that it's not the maximum theoretical limit. So your system might be just badly designed, and this is what everyone should remember from this talk, and then already go into the details. But this is exactly perfect point.
You've got your design choices, you've got your operational choices, and all of them come at the cost of efficiency. So make them wisely.
Yes. Thank you very much, and thanks for everyone for being with us on our 15th episode of Coffee on Compressed Air, and we see each other next week. Have everyone a nice day, evening, and morning. Thank you.
Bye, everyone.